Hi, and welcome to this final video in block 2 of TBMT42 on systems biology, digital twins, and AI. So the common denominator in all of this block is that we use data to inform the model and to learn things about the model. And in this final video, we're going to close the loop. So we're going to learn how to optimally generate new data, how to design experiments that give us the maximal amount of information. And we'll basically look at 3 reasons to do an experiment. One is to refine and improve certain aspects of a model. One is to test whether a model is good enough or not. And one is to distinguish between 2 competing hypotheses. So let's dive in. So we will look at the basic idea of how to do things. We'll return to the core prediction slide where we had the core prediction and we have the more uncertain side. And I will add some additional thoughts to that, and then we'll look at the concrete example. And that's basically it. After that, we will wrap up and we will look not only at this particular video, but at the entire block and look a little bit ahead at the remaining blocks. Okay, so core prediction slide. You saw this already. These are simulations for all the different acceptable parameter values, and here is well determined. So this is a core prediction, and here they are just suggestions. And again, if you just have a single simulation, they're all suggestions, they're all beach statements. And if this is all you have no idea what is a good reason to do an experiment. Because if you would suggest to measure something here or something here, that's 2 very, very different reasons why to do the experiment. So if you are measuring over here, then you can really test the model. And if you have 2 models and one is generating a very well-determined value here and some other model is generating a very well-determined value that is different, that is maybe down here, then this would be an excellent reason to distinguish between models because they have both well-determined predictions for this particular point that you want to measure, and they are different. So if you have the case that they are both acceptable, they can both describe all of the data that we have, then you know that if you do this one experiment, you measure this one time point, then you will be able to distinguish between the models. Something you cannot do right now, you will be able to do if you just measure this one time point. And even if you don't have 2 models, just knowing that this model is really sort of sticking its neck out to sort of say that, well, I'm certain that this is the value. If it's not this value that you will get over here, my whole existence is questioned. You should probably throw me away and pick another model. In contrast, if you would measure over here, you can get basically any value from very, very low values to all the way up to here, which is sort of the maximum value. And the model would agree with that. Or there would be some parameter that agrees. So if you look at the prediction with uncertainty, the uncertainty is so big that you will not be able to reject the model or test the model. However, you can use it if you know the parameters too little. If you think that all of the predictions that we have are too uncertain, we want to know the parameters, then you should measure here, because then you want to know which of these parameters is the true one. So if you want to determine the parameters better, then you should measure where it's as uncertain as possible. And if you want to test the model or distinguish between models, then you should measure where they are well determined. And that's why it's so important to have this uncertainty. Here you have no idea. And since you have no idea, if you get a different value, you don't know if that means that you should reject the model or simply that you happen to pick the wrong parameter. So you need to have predictions with uncertainty. You need to distinguish between core predictions and suggestions. Okay, fine. So let's just dive a little bit more into this. So if you want to improve the model is too unreliable or too uncertain, then you should measure something that corresponds to the left of the previous slide or the previous plot, where it's as uncertain as possible. Something you don't know, something the model doesn't know, then that's what you should measure. And the control engineering point of view of doing that is to do many small and combined perturbations. This is a normal way to determine the parameters better. But you can also just find a prediction that has a high uncertainty and measure that. So that's if you want to determine the parameters better and determine the model better. If you want to test the model, then you should predict something that you haven't got any data for. So that in principle is an excellent basis for an experiment. It has to be well determined, and the best thing is that if it's also something that's unexpected or unintuitive, it's very weird that you have this prediction with the model. Is that really correct? And then if you measure that and it is correct, then it's really evidence that the model has really gathered some valuable information, because its weird prediction happened to be true. And the final reason, if you have two models that both explain the available data equally well, you want to look for well-determined predictions that are different. And it has to note that it has to be more different than the uncertainty in the data. So it's not enough that they are different. If the data that you can get in this particular area is very, very hard to determine, so the uncertainty of the measurement data is very big, then it might be that the distance that you have is not big enough for you to be able to tell which model is correct. So you need to take that into account as well. Okay, so this is basically it. Now let's just have a look at an example. So I won't go through this in much detail, but in this particular case, in a paper that we published in 2010, we had 4 hypotheses for why an overshoot was generated. So you add insulin at time point 0, and this generates an overshoot. So we basically knew that we needed to have to explain this first data set, we needed to have some kind of negative feedback. So we formulated 4 hypotheses for a negative feedback. And since they had a negative feedback, they could all generate this overshoot, but they did it in fundamentally different ways. One by degrading the amount of insulin, one by downstream signaling, one by competitive inhibition at the membrane, and so on. So fundamentally different ways that all could generate the original data set. So then we wanted to design experiments. And the first experiment was to see how much insulin is degraded. And it turned out that the insulin degradation hypothesis had that you have to have a very rapid degradation, or more than 90% within the first half hour. And the others didn't have any degradation at all. So we had a very well-determined prediction for one of them that was completely different compared to the others. So we measured the amount of degradation, and it turned out that there was basically no degradation of insulin. So they couldn't all of them be correct, but we knew that by doing this one thing, the amount of degradation is so extreme in one of the hypotheses that we can't determine super precisely the value of insulin, but we can determine whether 90% has disappeared or not. And it turned out that there was no detectable degradation. Okay, so then in this particular story, we realized that there are basically no more core predictions. There are no other core predictions. So we need to determine the parameters better. So then we just added lots of data that was consistent with the models, but that had this sort of multiple predictions and like combinations of different doses and so on. So the typical control engineering type of thing of just adding more data that is perturbing the system in different ways. So then we didn't reject anything, because that was not the point. The point was to determine parameters better. And then we had core predictions. So then we could design new experiments that could incrementally reject hypothesis after hypothesis. And after a while, we only had one of the 4 original hypotheses left. So then we did a validation test where we wanted to say, okay, so now we need a well-determined prediction. Let's see if that is correct. And in this particular case, it was not correct. So all of the 4 original hypotheses had to be abandoned. So we had to formulate a combination of them. And that could describe all of the old data and also correctly predict new data. So that was the one that we sold. So we did 5 iterations in the systems biology loop. So this is a systems biology index 5. And this is the model. So it has this insulin binding to the receptor, the phosphorylation. It has the internalization, which is one of the feedback loops. But it also has another feedback, which is from some downstream signaling that increases the dephosphorylation. So you needed a combination of those. And if you don't have this combination, if you have some simpler version, you cannot describe all the data. So we could really pinpoint that these are crucial mechanisms. And each experiment had a very clear purpose that we knew what it was before we did the experiment. Okay, so let's zoom out. We are basically done with this loop. We know how to use data to formulate an estimation problem, to use either global or local optimization to get the predictions. And we know how to get predictions with uncertainty and parameters with uncertainty. And we know how to do statistical tests to know if we should reject the model or not. And we also know now how to design experiments to generate new data. So we basically know how to do this entire loop here now, how to draw conclusions from data, and including how to generate more data. So that's basically block 2. What we'll do now in block 3 is to assemble the digital twin. So we'll learn how to do hierarchical models, putting different submodels together into the multi-level model, how to make the model personalized using nonlinear mixed effect models. We already mentioned this a little bit, but now we'll spend almost a whole week on that. And then in the final week, we will do these hybrid combinations where we also combine it with AI to not be able to only be able to simulate this type of physiological variables like the adipose tissue glucose uptake, but the risk of a stroke, and how to combine it with bioinformatics type of approaches that also uses more machine learning, with imaging-based analysis, language-based models, and so on. So that's the final block. So we did the systems biology. Next week is digital twins, and the final is AI. Okay, so that's it for this video and for this block. Thank you for listening.